In this video, I'll discuss projectile motion problems. Model 4.1 describes projectile motion. For motion under the influence of only gravity, we model the object as a particle launched with an initial speed, v sub 0, at angle theta. Mathematically, this is uniform motion in the horizontal direction, with the x component of the velocity equal to v sub o cosine theta. Constant acceleration in the vertical direction is equal to a sub y equal to minus g. For both the horizontal motion and the vertical motion, we have the same delta t. Limitations of the model. The model fails if air resistance is significant. So on our problem-solving strategy for projectile motion problems, our model we adopt, is it reasonable to ignore air resistance? If so, use the projectile motion model. To visualize, establish a coordinate system with the x-axis horizontal and the y-axis vertical. Define symbols and identify what the problem is trying to find. For a launch at angle theta, the initial velocity components are v initial x equal v sub o cosine theta and v initial y equal to v sub o sine theta. When we solve, we know the acceleration. The x component is equal to 0 and the y component is equal to minus g. Thus the problem is one of two-dimensional kinematics. The kinematic equations are, in the horizontal direction, x final is equal to x initial plus v initial x times the time interval. V final in the x direction is equal to v initial in the x direction, which is a constant. The kinematic equations for the vertical component of the motion are y final is equal to y initial plus v initial in the y direction times delta t minus 1/2 g times the time interval squared. And v final in the y direction is equal to v initial in the y direction minus g delta t. You'll recall that I refer to this last equation as equation 1, and the upper equation, I referred to that in earlier lectures as equation 2 for kinematics with motion with a constant acceleration. We'll use this example to discuss reasoning about projectile motion. A hungry bow and arrow hunter in the jungle wants to shoot down a coconut that's hanging from the branch of a tree. He points his arrow directly at the coconut, but as luck would have it, the coconut falls from the branch at the exact instant the hunter releases his string. Does the arrow hit the coconut? Well, our reasoning goes as follows. Without gravity, the arrow would follow a straight line. Its kinematical equation would be y final is equal to y initial plus v initial in the y direction times delta t. And we know that if the motion is that of a projectile in a straight line. We know that its x component will have the equation x final is equal to x initial plus v initial x times delta t. Let's assume that y initial and x initial are 0. Then we see that y final as a function of x is equal to v initial y over v initial x times x final. And we have then the equation of y versus x as a straight line, as shown. But now let's turn on gravity. What happens to the y equation if we have gravity involved, the acceleration due to gravity? Then we have to add this extra term, minus 1/2 gt squared. So now our y equation changes from a straight line to the straight line and minus this negative term, magnitude 1/2 gt squared. This causes a separation between the straight line and the actual trajectory, and the separation grows as 1/2 gt squared, given the trajectory its parabolic shape. Had the coconut stayed on the tree, the arrow would have curved under its target as gravity caused it to fall a distance 1/2 gt squared below the straight line. But 1/2 gt squared is also the distance the coconut falls while the arrow is in flight. That is, the y position of the coconut is equal to v sub o yt minus 1/2 gt squared. But it's starting its fall from rest, so its initial velocity is 0. So y position changes as 1/2 gt squared. Therefore, both the arrow and the coconut have velocity vector in the y direction, their vertical distance getting smaller and smaller as 1/2 gt squared, their vertical height getting lower and lower as 1/2 gt squared. So yes, the arrow hits the coconut. Now we'd like to apply our reasoning to this example. A place kicker must kick a football from a point 36 meters from the goal, and half the crowd hopes the ball will clear the crossbar, which is 3.05 meters high. When kicked, the ball, not the call, but the ball, leaves the ground with a speed of 20.0 meters per second at an angle of 53.0 degrees to the horizontal. Part A of the example asks, by how much does the ball clear or fall short of the crossbar? And part B, does the ball approach the crossbar while still rising or while falling? So when we work this problem, we'll model the football as a particle. And we visualize its motion with the figure to the right, where I've drawn y as a function of x. And I show on the horizontal direction the location x1, which is the location of the crossbar, and y1, which is equal to h, the height of the football goal. So let's now recall what information is known. We know that the initial position in the x direction and the y direction and the initial time are all equal to 0. We also know that the initial velocity, as shown in the figure, has a magnitude of 20.0 meters per second, and the launch angle theta is equal to 53.0 degrees. And the acceleration is only in the y direction, and that's equal to minus g. We're told that the height of the goalpost is equal to 3.05 meters, and the horizontal direction at time t1 is equal to the horizontal position x1 at t1 is equal to 36.0 meters. So what do we want to find? Well, part A, we want to find what is y1. Is it greater than h or less than h? And then in part B, we want to know if the ball is on its way up or rising, when it gets to the goalpost, or is it falling? So let's write down our equations. For the motion in the x direction, we know that x1 is equal to x initial plus v sub o x t, where t is the elapsed time, or the time when the ball is at x1 and y1. And we know that x sub 0 is 0, so we can write this as v sub o xt, and this is equal to v sub o times the cosine of theta times t. We can call that equation 1. And then equation 2 is for motion in the y direction. Well, we want to find out what its vertical position is at time t1 or t. So we have y sub 1 is equal to y sub 0 plus v sub 0 y t minus 1/2 gt squared. And we know that y sub 0 is 0, And v sub y is equal to v sub o sine theta sub 0, or sine theta. And this is multiplied times the time, minus 1/2 gt squared. We'll call this equation 2, which we want to solve in order to answer part A. But we don't know what the time is directly from this equation, so we have to use our equation 1, solve for the time, and then plug that into equation 2. So let's do that. T is equal to x1 over v sub 0 cosine theta I'm going to put in the numbers now. X1 is 36.0 meters over 20 meters per second times the cosine of 53.0 degrees. This is equal to 36.0 meters divided by 12.0 meters per second. So we find that our time is equal to 3.00 seconds. Now we can use this result. We can take this value of t and insert it into equation 2. And when we do, we get y1 is equal to v sub o sine theta, which is 20 meters per second, sine 53.0 degrees, times the time, 3.00 seconds. And then we subtract from that 1/2 times 9.80 meters per second squared times the time, which is 3.00 seconds, and that has to be squared. All right, let's calculate these two terms. When I evaluate 20 times the sine of 53 degrees, I get a v sub y of 16.0 meters per second. Times 3 seconds. And when I multiply 1/2 9.80 times 3 seconds squared, let me perform that calculation. I get 44.1 meters. So if I finish the calculation, I find that y1 is equal to 3.90 meters. And when we compare that to the value of h, the height of the crossbar, we see it's greater than h. Okay, so that solves part A of the problem. Then in part B, we want to know, is the football rising when it gets to the crossbar? Still rising? Or is it on its way down? Is it falling? So if it's rising, that means that the vertical component of its velocity is pointing up, or is positive. And if it's falling, it's pointing down. So let's just solve for that final velocity and see what the sign is. So V final y is equal to V initial y minus gt. And we calculated V initial y in the previous step. We found that it was 16.0 meters per second. And then we subtract off 9.80 meters per second squared times the time, 3.000 seconds. And when we do, we see that the final velocity is minus 13.4 meters per second. So that tells us that the final velocity has an x component of 12 meters per second. And a y component of 13.4 meters per second in a negative direction. So the final velocity is pointing downward in that direction I'm showing now. So it's falling. And that concludes this problem and concludes this video.